In this chapter, we will look at traditional cup and cone bearings, cartridge bearings, tools to install and remove cartridge bearings, cartridge bearing dimensions, the ABEC rating system, and steel versus ceramic bearings.
When you're doing some product comparing and it comes to good hub repairing, there's no debating. Use the ABEC rating in search of a quality bearing. This chapter is about hubs and hub bearings, and it may surprise you how in-depth the topic of bearings is. I'm going to give you a little bit of a view into that topic and cover some of the basics, but people spend their entire lives designing and getting to understand better bearings in bicycle wheels.
Let's begin with a question. What makes the world go round? Well, it depends on who you ask. If you ask Aphrodite, she'll say love. If you ask me, I'll say bearings. This is one type of bearing where I have loose balls in a cup and cone system. On the left, we see the rather bowl-shaped cup, and on the right, the cone. Here we can see the cup inside the hub shell, and we see a cone on a threaded axle, and that is the depiction of one of the balls. The balls will be trapped between the cone and the cup when the cone is screwed in. The balls are provided in either of two ways. On the left are loose balls, and on the right are balls inside a retaining ring. When I use loose balls, I can get 9 of them in the space between the cup and the cone. When I use a retaining ring, there are only 7 because part of the space is taken up by the retaining ring that keeps the balls separated from each other. For that reason, mechanics generally prefer the loose ball system because it provides better support than a retaining ring. The retaining ring, on the other hand, is a little bit easier from a manufacturing standpoint. Here's a nice schematic from the Park Tool Company showing all of the pieces of a cup and cone system. The other type of bearing found in bicycles is a cartridge bearing. Unlike the bowl-shaped cup that accommodates loose balls or a retaining ring, in the case of cartridge bearings, you have a right angle here and parallel sides. That means we have to use loose balls or retaining rings in the case of the bowl-shaped cup, whereas in the case of the other kind for cartridge bearings, we use this type of a system here, and they are not interchangeable. These are 3 beautiful hubs: the Velocity Race Hub, the White Industries T11, and the Chris King R45. These are the kinds of bearings, cartridge bearings, that are used in those hubs, and we're going to define those with 3 different dimensions. These dimensions will all be in millimeters. This is the outside dimension. The inside dimension, we have a width of 9 millimeters. This bearing has an outside diameter of 30 millimeters, an inside diameter of 10 millimeters, and a width of 9 millimeters. So its definition is 30 millimeters by 10 millimeters by 9 millimeters.
For years, I taught a class in bicycle maintenance, and on the first night of the class, I asked my students the following multiple choice question. The question was this: the standards for dimensions in bicycles are A, all metric sizes, B, English fractional sizes, or C, a mixture of metric and English sizes that seems arbitrary and confusing. Here's an example.
With cartridge bearings, as we saw, the 3 key dimensions are in millimeters. But the dimensions of the steel balls themselves are fractional inches, such as 1/4 inch, 3/16 inch, or 5/32 of an inch. Just follow the arrows and I'll explain here to you what we're looking at. This is a cartridge bearing. This is a seal on one side of it that I've removed, and that exposes the inside. Now this little piece here that broke on this bearing is intended to keep the balls separated equal spaces from each other. Without that, there's nothing to keep the balls from moving around and losing the equal spacing, and once that happens, then the integrity of the cartridge bearing is destroyed. On the left is that same broken cartridge bearing, and you can see the piece of the spacer that is broken off. On the right is a ball that I've removed from that bearing, and I'm using my micrometer to measure its dimensions, and the ball is 5/32 of an inch. And if you divide 5 by 32, you'll see that comes out to 0.156 inches. So the ball itself is measured in fractional inch size. Here's a picture of a really high quality cartridge bearing from which I have removed the seals so we can see the inside. Note all the grease that is keeping the bearing properly lubricated. The cup and cone system shown here is really pretty easy to work on if you're a home mechanic. Easy to take it apart, re-grease it, put in new balls, replace a cone if necessary. On the other hand, the cartridge system on the right requires special tools to remove and install the bearings. This bearing press sold by Wheels Manufacturing is the best one I know of, and it was actually designed by a fellow named Jeremy Parfit of Alchemy Bicycle Works. All these adapters of various sizes allow any kind of a bearing to be pressed on carefully. To get bearings out, you need a bearing puller, and this one by Motion Pro is the best one I know of. It comes with a slide hammer to give you a lot of mechanical advantage, and then you attach to the slide hammer whatever size collet you need to fit inside the bearing. There's an organization called the American Bearing Manufacturers Association, and within that there's a committee, the Annular Bearing Engineering Committee. Annular, not angular. Abbreviated ABEC. An annular ball bearing is a rolling element bearing designed primarily to support a load perpendicular to the shaft axis. The key terms here are load and perpendicular to the shaft axis. There's a nice White Industries hub. There's the shaft axis, the load pushing down on it, and there are my bearings arranged perpendicular to the shaft axis. We want to look at the type of cartridge bearing used in this hub as well as what is used in the matching front hub. One of the bearings in the rear hub is a 6902 bearing, and it has these dimensions, and these are the specifications. It's an ABEC 5 bearing, which I'll explain in a minute. The other type of bearing in the rear hub is a 6802, and it has these dimensions and these specifications. Once again, a really nice Enduro ABEC 5 bearing. The front hub has two 6901 bearings, those dimensions, and these specifications. Inside my White Industries T11 hub is a 15 millimeter center axle, and we're going to use these bearings in 3 locations. The 6902 is represented by that blue rectangle, and we have 3 of them, here, here, and here. What White Industries did initially was to use, in addition to the blue bearing shown, a 6802 bearing, actually 2 of them shown in green, and these were 2 bearings that were butted up against each other. Now, however, instead of using 2 5 millimeter bearings side by side, now they use a specially made bearing made for them by Enduro, and it's a 3802 bearing with a width of 10 millimeters. In my front hub, I have a 12 millimeter center axle, and I'm going to use a 6901 bearing on either end of it, and we'll show that in red, one here and one here. In all of these bearings, the inside diameter of the bearing is the same as the outside diameter of the center axle. That is 15 millimeters for the rear hub and 12 millimeters for the front hub. This is that same bearing you saw a few minutes ago with the seals removed to reveal the inside of it. I've removed all of the grease so that we can clearly see the action as the bearing spins. This is an annular bearing supporting a vertical load, and as the bearing turns, the balls inside support the bearing between the races. Just to give you a peek into how specific some standards are, we're going to look at a couple of annular ball bearings and see what the ABEC standards are. There's a whole set of standards for the tolerance for eccentricity of the inner racetrack. If that's our bearing, that is the inner racetrack there, and we can make a little table, the ABEC scale, the maximum allowable eccentricity in millimeters, the maximum allowable eccentricity in inches, and then something called the ISO 492 scale. Let's start filling in the table. Here is the ABEC 1 bearing, and you can see the maximum allowable eccentricities, and over on the right in the ISO 492 scale, this is called a Class 6X bearing. This is an ABEC 3. And as we go down this list, we will see that the bearing is engineered to more and more specificity in the dimensions. Here's an ABEC 5, an ABEC 7, and an ABEC 9. Now let's look specifically at the ABEC 5 bearing. In discussing my ABEC 5 bearing, let's first start with some type of a dimension that is absolutely perfect in roundness with as much specificity as we want. So we're going to say that the diameter here is 25.000 with as many zeros as I want to put after it, and likewise in this dimension also. So this is perfectly round to infinite specificity. That, of course, is not achievable. The ABEC 5 bearing comes pretty close, though. So I have a tolerance around that exact 25 millimeters of 0.0035 that I allow myself in any dimension for the diameter to be that much more or less than exactly 25. So you can see there on the right that I have a very small allowable variation from the exactness of 25 millimeters. As highly engineered and manufactured as the ABEC 5 bearing is, the ABEC 7 and ABEC 9 are even more so. That doesn't mean that they would be appropriate or necessary on a bicycle, however, but in some type of an orbiting spacecraft, you might want to use an ABEC 9 bearing. Highly detailed standards are also published for the outer ring size tolerances and inner ring size tolerances. There are also standards for the roundness of the balls themselves in a ball bearing, and we'll make a table once again. The ball type, the grade scale, and the tolerance for roundness in inches. And we'll start filling in our table in the middle, showing chromium steel grade 25, which means that it has to be accurate to within 25 1/millionths of an inch of roundness. Here's chromium steel grade 10, accurate to within 10 1/millionths of an inch, and chromium steel grade 5 to 5 1/millionths of an inch. If we go back and look at the standards for the bearings used in those White Industries T11 hubs, you'll see down here that they all use ABEC 5, grade 5 chromium steel balls, so that there is a very high accuracy in the roundness of the steel balls that are used inside the cartridges. Let's continue filling in our table with a ceramic silicon nitride ball, grade 5, same roundness as the chromium steel grade 5 ball. And I can also get this even with a finer accuracy, a silicon nitride grade 3 ball, accurate to 3/1 millionths of an inch in roundness. Now, as I go down this table, the cost, not surprisingly, goes up. Let's, back at the top, add a few more in. A chromium steel ball grade 300, accurate to 301 millionths of an inch. And just for a little bit of humor, we'll assume there's a grade F made out of El Cheapo steel, and its accuracy is better than a pebble. Sometimes the specifications of bearings are printed on the side, as we can see here, and if we look closely, we note that this particular bearing is an ABEC 5 bearing. Now, as a little aside here, let me mention a couple things about ceramic silicon nitride bearings with a formula of Si3N4. They are highly resistant to corrosion, and let's see why that is. Okay, so the chemist in me has figured out a way to get the periodic table into this, and we're going to look at this quickly here. In dark blue, we have metals. In the middle section, we have the transition metals. We have more transition metals down at the bottom. Those are intertransition elements or rare earth elements. In green are the metalloids, and over here on the right are nonmetals in yellow. Here is silicon, right under carbon, and up here is nitrogen. If we could imagine an individual molecule of silicon nitride, it might look like this, with a silicon atom in the middle, and on each corner of a regular tetrahedron, one atom of nitrogen. But in fact, it does not exist as individual molecules. It exists only as part of a complicated lattice structure, which has, on the average, 3 silicon atoms for every 4 nitrogen atoms. If you're interested, you can check out some of these references. I'll tell you that there's an extraordinary amount of detailed information in there, but it's there if you want to root it out.